Good morning. Suppose we have a circuit like this and we are asked to calculate line currents, phase currents and the power delivered, the losses in the lines and the power absorbed by the load. So here the first thing to do, this is a balanced three-phase circuit. We have to transform this triangle or delta circuit to a star, and then the currents can be easily calculated. So let's transform the delta into a star. So we will have following circuit. Let's say phase 1. Here we have 0.5 ohms resistance of the line, J 0.4, and the delta, which is transformed to a star. This is a neutral. This is the neutral of the load because it's balanced, so it means these neutrals are at same potential. So here 24 divided by 3 will be 8 ohms, and here it will be 18 divided by 3, and it will be 6. So we can calculate I1. This is V1, and V1 is given as 120 40 degrees volts, and I1 can be calculated as V1 over the line impedance plus the load impedance. So it's 120 40 degrees over 8.5 plus J 6.4, and in polar form the impedance is 10.6 for 37 degrees. 120 40 degrees will give us a current of 11.3 degrees, and from here we can calculate I1 and I2. I2 is we can write this expression, following expression, that I2 is I1 times 1 and phase angle. So it means that I2 is delayed with respect to I1 by 120 degrees. We can write this expression, and I3 will be 120 because it's leading. I3 is leading the phase 1 current, and that's the value of I2. We can calculate this. This would give us 117. It means we'll have 11.3 and minus 117, and here we will have 120 plus 3, so it means 100 argument will be 123 in amps. These are amps. Now we can calculate we have an expression between the line voltages and the phase voltages. We have square root of 3 plus 30 degrees. This is the expression between the line currents. We have also an expression between the line currents and phase currents, which is the following. So it means that it's square root of 3 minus 30 degrees. So it means the line currents are delayed by 30 degrees with respect to the phase current, and we can also calculate the phase current with respect to line currents, and it will be I, the line currents, over square root of 3 minus 30 degrees, which is, we can write the following expression. It's the line currents over square root of 3 plus 30 degrees. And knowing the line currents, we can calculate the phase currents, which I'm going to calculate here. Let's write the line currents first, which I have calculated. Point, 3 degrees. I2 is 11.3 minus 117 degrees in amps, and I3 is 11.3 plus 123 degrees in amps. Now we can calculate the line phase currents. I12, I23, and J31. As I said, it's 1 over square root of 3 plus 30 degrees times I1, and here it's 1 over square root of 3 plus 30 degrees I2, and here 1 over square root of 3 plus 30 degrees times I3. So it means we have following values which we'll calculate. So it's 11.3 divided by square root of 3 will give us a value of 6.524. Argument 3 plus this will give us 30 degrees in amps. 6.524 point, excuse me, I use comma instead of point. Here will be minus this plus this will give us 87 degrees, 24 and 153 degrees in amps. We have calculated the phase currents. We can calculate the power delivered by the source, which is 3 times V1 times conjugate of I1, and it's 3 times 120, 40 times line current, which is 11 point conjugate minus 3 degrees. This will give us a power of 4068 and 37 degrees volt ampere. We can calculate the active power. This times cosine 37, 3449 watts, plus the reactive power 2004 for 8.2. These are watts and these are bars. And we can calculate the power absorbed by the load by calculating the losses on the lines. So the losses, SL, are 3 times the drop, voltage drop, times the conjugate of the current. We can calculate delta V, and this is line impedance, which is 0.5 plus J04 point times I1, and this will give us 11.3 degrees, and here in polar form 38.66 times 11.3 3 degrees, and the result is 7.232 and argument 41.66 in volts. And from here we can calculate the losses. So the losses are 3 times the voltage drop, 0.232, 41.66 times the current conjugate of the current, and this will give us the losses is 245.16, 38.66. These are volt-amps. Active power will be 191.44 plus J, 153.15, and we can calculate now the load power. It's the source power minus the losses, so it means it's 304.49 minus 191.44. This is the active power plus J, and here we write the reactive power minus 153.15. So let's calculate the result. The load power taken 3,449 minus 191.44 will give us power of 3,257.56. Reactive power 2448.2 minus 153.15. That will give us 2,295.05, and that's it. We calculated everything, and thank you very much.